All right, cool. So go down, we have these different rules for types of association. So all of these, it's the same transversal, and it's explaining how angles of certain parts associate with one another. So here you see that 4 and 5 are identified in the very first row. And if they are, well, the name is alternate interior angles. You don't have to know that name or anything. The rule is that these two are equal. That's it, they're equal. So although they're spaced out as such, that's one of the properties of a transversal. There's certain associations between these angles that we can make. And we're going to apply this in the next problem. So those were alternate interior angles, interior being inside. Exterior angles have the same property, it's just equal. That's it. So it means if you have two angles that are positioned as such on a transversal, then they're equal. You can kind of tell based off of their sizes that they're at least close to each other, but this asserts that they are in fact equal. So what about interior angles? The next one. You can definitely tell that 4 and 6 here are not the same size. 4 is definitely larger than 6. So I won't be writing equal. Instead, I'll say 4, 6 are supplements, or supplementary. So hopefully you remember what supplementary means. We talked about that in the last class. They add together to give you 180. As you can kind of tell, 4 doesn't go all the way. So 4 doesn't stretch out all the way. It's got that missing piece right here, and 6 will fill it perfectly. And then the final one, what about corresponding angles? Angles in the same spot but different position. There you go. So that's pretty much it. You can kind of look at them and tell by their widths whether they are equal or supplementary. Mainly the supplementary one is probably the only deviating idea here from, well, this equal intuition for a lot of these. And we're going to look at a few of these associations down below. On the measures of the angles in the figure below. So here, this is all the information we're given, and we are, so according to the premise of the example, we're going to be able to find all the angles. So if anything, well, there's a little bit of information we can utilize here. These positions help us consider, well, what is equal or supplementary here? Well, if anything, we only have quantitative values for 1 and 4, even if they are symbolic. But that positioning in example 1 between 1 and 4, so if we scroll back up right quick, 1 and 4 are examples of corresponding angles. It may not seem like it, but they are in fact corresponding angles. It's just not positioned in the specific manner, but they really are corresponding angles. So, as such, since they are corresponding, then we know that 1 and 4 are equal. And since they're equal, well, what's 1? 3x plus 2. What's 4? 5x minus 40. So since they're equal, we just set up an algebra problem. We can solve for x. I'm going to breeze past this. We combine some like terms together, and we get that x is 21. But that, just because we finished a sequence of steps doesn't necessarily mean that that is the final answer. In fact, we're not even close in terms of presentation. So angle 1, it was 3x plus 2. So now it's 3 times 21 plus 2.
65.
65. So 65 degrees. And so angle 4, we don't even have to solve for this algebraically. They're equal. Is that good so far? And so now we're left with 2 and 3. Now, if anything, between 2 and 3, one of these is, well, easier to figure out than the other. 3 corresponds to 1. 1 and 3 are corresponding angles. And as such,
So it'd be 180 minus 65 would give us.
That's right, for the last one. So 1, 4, and 3 are all, in fact, equal. They're all corresponding angles. That just leaves angle 2. So the association with angle 2 is, well, it is supplementary to angle 1, or equivalently, it's supplementary to angle 3, just by virtue of the fact that they correspond in that particular way, and their sum gives you a straight angle, as we called it. So angle 2 is simply 180 degrees minus the 65 degrees we found. So what is that? It's like 115 or something?
Yeah.
So that would be the 4. So that's angle 1, angle 4, angle 3, and angle 2. They're pretty straightforward. Google Meet people, awesome. All right, cool. Let's move on. So some of you may be familiar with this property. The sum of the measures of the angles in a triangle are, the sum is 180 degrees. You might know that already from high school geometry. You might not. If so, here it is. If you take all 3 angles in a triangle and add them together, you're always going to get 180 degrees. And so that brings us to example 2 here. What is the sum of the acute angles? So remember, acute are the narrow angles in a right triangle.
45.
Well, not quite. You might be on the right. I think I see how you're thinking about it. Let me use a diagram, and I think you'll figure it out. So, all right. Let me try and actually draw a legitimate. That should be a right triangle, I swear. A right triangle, of course, it's got a right angle in it. That makes the other 2 acute. So if we know that the sum of all the angles is 180, and one of the angles has to be 90, then 180 degrees minus 90 degrees would tell us the sum of the other 2 angles, 90 degrees. So that would be the sum of the other angles in a right triangle. We will be utilizing this later for figuring out angles of a right triangle. So this is a pretty intuitive idea, because this 90 degrees comes from the right angle, and 180 is the total. So that's the sum. Example 3 kind of applies this a little bit further. They give us 2 angle measures, and we have to figure out the third one. So exactly what I said before. So if we know that all the angles add up to give us 180 degrees, so you might already see what to do. I'm going to write it out with a an intermediate step. I just realized I can rest my palm on the screen and write. So, okay, that's going to make writing so much easier now. Awesome. So that one and that one plus a third angle, we don't know what it is equal to 180 degrees. Again, you might already see how to do this. It's an algebra problem. Naturally, we solve for x. So very similar to the setup of the previous problem, we take 180, and we're going to subtract everything I just wrote. Now you might think, oh man, I have to do that in the calculator now? Wasn't subtracting the degrees, minutes, seconds a pain? I told you how to do it in the calculator. So guess what? You get to do it in the calculator. So I told you how to put degrees, minutes, seconds in the calculator. And by being able to successfully do it in the calculator, again, I'm not going to show you how to do that right now. You can ask me after class if you get tripped up, but 180, and you don't have to put the degree symbol for the, actually, let's be safe. I'm going to put the 180. So 180, and I'm putting the degree symbol, just to be safe, minus 147 degrees, 12 minutes, minus 30 degrees, 19 minutes. And if you did it correctly, again, if you didn't do it correctly, I implore you to figure it out on your own and then ask me. So my calculator gives us 2.483 repeated. And really what this problem should tell you is to put this answer in degrees, minutes, seconds, because the other two are in degrees, minutes, seconds. So how do you convert from this degree to degrees, minutes, seconds? Well, I showed you how to do that yesterday as well. You have to use that arrow DMS button in the calculator. Again, I showed you how to do that yesterday. And then you would get actually a precise answer. 2 minutes, or 2 degrees, 29 minutes.
I think it was a decimal. Can we write the decimal? How do you want to round up? Because it gave me 2 degrees and 28 seconds.
What did you type into the calculator?
2.483.
So what I did was with the answer,
You just used the answer that it
I
gave.
used the answer straight. So for those of you, so when I got the 2.48333 in the calculator, I left that result on the calculator. And while keeping that on, I found the DMS conversion button, and it will do it exactly for you. Again, if you messed up on that, either try to talk to each other in the chat about it. So if not, then just ignore what I'm saying. But if you get 2 degrees and 29 minutes, you're good to go. If not, try to figure that out. All right, example 4. This is a pretty standard problem. Find the measure of each marked angle, and we have a triangle. So we know something very interesting about the angles in a triangle. The angles add up to give you 180 degrees. So here, x is one of them, x plus 20 is another one, and 210 minus 3x is another one. That's us adding all 3 of these angles together, just like that. And guess what? We have an algebra problem. So pretty simple algebra, it's just a linear equation. So let's see, I see an x and a minus 3x, so that's minus x plus 230. So yeah, 2x minus 3x is negative x, and plus 230. Subtracting 230 on both sides, or equivalently x is equal to 230 minus 180 is equal to 50. So we found that x is 50. And so now that we have x is 50, we're not done yet. We just have to figure out the angle measures themselves. Well, this one solves itself. That one's just 50 degrees because it's just x by itself. Obviously, this one's 70 degrees because it's just 50 plus 20. And the bottom one is probably, I don't know, something. What's 60? Once you plug in 50 for x. So those would be your three answers, 50, 70, and 60. In class, people, how do you feel about that?
Through 130.
Yeah, we're not 1 through 130. Yeah, do 1 through 130. I changed my mind. Let's do 1 through 130. Do every problem in the book. Let's just have that due tomorrow.
Yeah.
Yeah, just look at the top of the notes. I always have, and I sent it out in the email as well. You got to read the emails. So sent it out in the email as well, just to specify. So, yeah, you can see at the top of this page for section 2, I have, so notice, homework, right there. All right, cool. Let's keep going. So, types of triangles. This might be straightforward. An acute triangle, all the angles are acute. So if I say acute triangle, that's what I refer to. A right triangle, you might all be familiar with. Just one right angle. Obtuse angle. One obtuse angle in a triangle makes it an obtuse triangle. And hopefully you know what an equilateral, isosceles, and a scalene is. I think they teach that in grade school. So if not, there's the criteria right there. I'm not really going to dwell on it. There'll be quick terminology that may be thrown in. So for example 5, let's just try to think if we can construct examples of the following descriptions and see if we can make any example of a triangle that fits those descriptions. We start off with an isosceles right triangle. So the question is, can we do that? The answer is, yeah, we can do that. Isosceles means two of the sides have to be equal. The right triangle has 2 legs and a hypotenuse, which we'll talk about later on. So these 2 sides can be the exact same, and then the hypotenuse would be a different one. And normally we notate equal sides. As you can see in the description above, sides that are equal, we give them the corresponding number of dashes. If they have more than, if they don't have the same number of dashes, then they're not equal. Like in that scalene triangle illustration I have. So that one can happen. What about an isosceles obtuse triangle? So not a right triangle, an obtuse triangle. The answer, yes. So we can make a really wide triangle, really wide, where these 2 segments are the same, and we just close it off, just like that. So that one can happen. So what about an equilateral right triangle? Equilateral means that all the sides have to be the same length. Right triangle, So let's think about this. If I were to draw out a right triangle, then the hypotenuse, which you will slowly learn is this slanty line right here, is always bigger than the corresponding legs, which is this one and this bottom one down here. The hypotenuse is always larger than the other legs. Again, we'll see that more. I mean, this is trig. We're going to see that way too many times. So this cannot happen. So, nope. Can't happen. Or I guess if you want to be technical, just say impossible. Possible. There we go. Cool. And then finally, a scalene acute triangle. The answer is yes. I drew one up here. So that is a scalene acute triangle. So you can't have that. So just think about that. So that's 4 examples right there. So mainly that's terminology-based stuff. In-class people, anything, meet people, cool. All right, let's keep going. All right, we get to something a little bit more significant. Similar and congruent triangles, mainly similar triangles. Similar triangles, it's the same shape, but not the same size. So it's basically, you take one triangle and you scale it either larger or smaller. Similar triangles, the reason why we give it a fancy name, similar triangles have the same angle measures, but the lengths are going to be different. I mean, that's why one triangle would be larger than another, but they would be they're still considered similar. So, what were the examples I had? I wrote down the examples in my notes. Below are some examples of blah, blah. Okay. So, the examples I had, so A and B, these are going to be similar. So, one would be, say, a right triangle. So that is a right triangle. Again, it's tough to draw line segments on this thing. So notice that the top angle has a single arc and the other angle has 2 arcs. That means they're different angles. Very similar with how we do that for sidelines. And then another triangle, much larger. Still a right triangle. And I'm going to put the same arc, the same arcs. And so what this means, although one triangle is definitely larger than the other, which means the segments, the length of the segments will be different sizes, the angles are the same size. That's what that means. Just because the triangle gets larger doesn't mean the angles get larger. So that's what similar triangles represents. Part B. Oh God, this one's even worse to draw. Okay, so something like that. It's a scalene triangle, which will be represented by one having a single arc, the top one having 2 arcs, and the bottom one having 3 arcs to represent that they're all different sizes. And then we're going to make that much larger. But the angle sizes are the same. Finally, part C, congruent triangles. Congruent triangles mean they're the same triangle. It means that the shape is the same and the size is the same, which means it's just an exact duplication. So we're not going to really talk about congruent triangles, but it's the same exact triangle. Same shape, same size. So A and B are both examples of similar triangles. Part C is two congruent triangles, which means they're the same. So that establishes some terminology and some examples. And below, we'll see why that's actually significant. Why do we actually care about that? So it's because of this property. The corresponding sides of similar triangles are in proportion. That sounds kind of technical. Let's try that again. The ratio of the corresponding sides of similar triangles have to be equal. Okay, I guess it's a little better. Let's see it in an example. Example 7 here wants us to find the unknown side length. And it says that these triangles are similar. They intentionally wrote it in a very wonky way, but seeing how we know that the right triangle is positioned, of course, here and here, we can rotate one of the triangles and make them, oriented in the same way. So if we were to take this diagram, take the two triangles and write them side by side. Let's go ahead and do that first. The first triangle is pretty easy. I think that one's in a pretty clear format for us. So I'm just rewriting that triangle on the left. I think that one's pretty straightforward. It's that bottom right triangle that we're going to reorient it and make it orient the same way as the other one. So you can definitely tell it's larger. We'll put the right angle there. And now we need to figure out what goes where. So if anything, definitely the 9 goes on the slanted line. That's the hypotenuse. It's right across. So it's right across from the right triangle, or the right angle. And then X is going up and down relative to the right angle symbol. So X would go right here. So now we have reconstructed the triangles to where, so we're told that they're similar, so we don't have to try and guess that. We're told that, which means that the corresponding sides, the ratio of the corresponding sides has to be equal. So what do I mean by that? What are the corresponding sides here? Well, 4 corresponds to X because they're on the same side of the similar triangles. So the ratio of those two, 4 over X, is the same thing, so equal, the ratio of the other corresponding sides. Just like that, 6 and 9. They correspond to one another because they're both on the hypotenuse, or the slanted line, of the right triangle. So once you have that, well, you can go ahead and cross multiply. And so it's just algebra from here. X is 6. So that's one of the, I guess, that's one utility of determining similar triangles, is that you get, well, you get these ratios that can help you determine a missing side if you know all the other sides. And we do have an example problem ahead, an application problem that sort of allows us to see this in a more practical perspective, how it may be helpful. So in-class people, good, bad, okay. Yes, I know I'm presenting. Okay. So, cool. So example 8 here. Forest fire, lookout tower, cast a shadow of some stuff. Okay, so it's a word problem. That already kind of bumps me out a little bit. I'm not a big fan of word problems, so I draw pictures naturally. So let's just try and visualize what's going on here. Okay, so a forest fire lookout tower. So, all right, tower. Here's my tower. It casts a shadow, so something about the sun. Just put a little sun here. My drawing's horrible. So it casts a shadow, so if this tower projects a shadow, that shadow is going to be right here. Because of course, the shadow cannot project into space. Where's a shadow normally at? Well, generally the ground. You know, of course it could reflect onto the wall or something, but I don't know. So that's the shadow, which is 180 feet long. Simultaneously, the shadow, so same sun, just different object. So there's a truck. No, beautiful truck. It casts a shadow. In fact, let me draw this a little bit larger so my text doesn't overlap with stuff. So here's a truck. Okay, cool. So truck. It casts a shadow of 9 foot, so same idea. It projects a shadow of 9 foot, and the truck is 15 feet long. So you can use all of this information to figure out the height of the tower. So here's the tower. We don't know it. We don't know the height of the tower, but we know everything else. So we can use this information alone because measuring the height of a tower, it might take a little bit of time, but we can use this, this idea of similar triangles to sort of get a good idea. Well, in practice, this would be a rough but pretty close estimate. Of course, in our example, it's going to be exact. And so now we can set up a ratio. So, in fact, I don't know why I call it a question mark. Let's call it X, because it's math place. It's called X. So what are the corresponding sides? X and 15 correspond. They're the two heights. So that ratio, let me write it here. That ratio is equal to the other, the ratio of the other sides, the two shadow values. And you cross multiply again, all that fun stuff. I'm running out of room, so I trust you all know how to solve from here. And you should get, is it 108? Did you get 108? All right, let me work it out.
It's 300.
You got 300? All All right, let me just work it out anyway. Okay. 9x is equal to, what's 15 times 180?
2,700.
2,700. Oh my, what did I do in my notes? I'll switch 9 and 15 in my notes. Okay, I did it right on here though. Okay, wait, okay. I bet you're all screaming at me in the virtual thing right now. Or no, yes, 9-foot truck. Oh my goodness, wow. All right, I bet you were all screaming at me in the virtual chat. I don't even want to look at it. All right, let me try that again. That's 9 foot. That's 15 foot. I'm so sorry about that. Okay. I even have it written down in my notes right here. So I swear I was trying to be prepared. Okay, so that one should be 9, that one should be 15. That's me just having a brain fart. So 9-foot truck, 15-foot shadow. All right, so X and 9 correspond, 180 and 15 correspond. And if you do that computation, you should get X is the 108 that I had in my notes. And let me definitely check that. Okay, I get 108. Oh, how embarrassing. All right, cool. We got that disaster out of the way. Let's see how bad you all yelled at me. Yeah, okay, so this is why we don't like word problems, exactly. I mean, I prepped right before class and I still got it wrong. So, all right, that was my fault. All right, cool. So, ignoring that, is everyone good? Besides from my misinterpretation. Awesome. So, the 108, again, that's the answer. That tells us that the height of the tower is 108 feet. And that's a good way of measuring it by not actually trying to scale the tower and try to figure it out in some exhaustive fashion. All right, cool. So we move on. Okay, so I guess before we move on, I wanted to emphasize problem 17 from the homework. I would like to go ahead and also assign this homework for Tuesday. So the homework for this also is due Tuesday. So I want to emphasize problem 17, as I mentioned up here. So if you look in your book, I'm trying to see where I can draw this out at. But if you look in your book at problem 17 in section 1.2, it's on page 16 in your textbook. Let me find a place to draw it. Is there any place in my notes I can draw it right quick? I'll fit it in right here. Because when I assigned this over the summer, students, I think almost every student got this one wrong because of lack of context. So it's some triangle. And really, it's the part that says 9x plus 12 degrees. It's that part. Everybody, from when I taught this class, so the other two angles are okay. But everyone assumed that this angle right here corresponded to the inner angle in the triangle. It does not. In fact, let me erase this so I can point to where it actually refers to. that angle that I just had refers to this exterior angle. So this is where the, what was it, 9x plus 12 degrees? It refers to that angle right there, not the interior one. The other ones refer to their interior counterparts. But that part in red, that refers to that angle. So it makes the problem more difficult. So that's the challenge problem of this homework set. That one and probably 65 as well. The rest of them should be pretty easy. They should follow along with the notes almost identically. So yeah, that's all I wanted to say, just right there. All right, cool. All right, so let's go ahead and move on. So again, that's my hint for 17, or just more so clarification. Let's move on to trigonometric functions. So this is where trig really in fact, this is where we start talking about trig instead of just geometry, really. So trigonometric functions. So this is probably the part of trig you're familiar with in terms of SOHCAHTOA and knowing what, at least hearing of what a sine or a cosine thing is. This is when we start talking about it. So the way we start talking about trig functions is how trig and the geometry, the underlying geometry, work together. So for the trigonometric functions, the way we start off the definition, we pick a point other than the origin. On the terminal side, all right, so a bunch of very technical stuff. So we pick a point in the XY plane. This point will tell us where our, and I'm gonna draw this out in example 1. In fact, let me go ahead and do that simultaneously. Let xy be a point other than the origin. In example 1, they give us a point other than the origin. So what I'm going to do, I'm going to construct a graph, an xy plane, and hopefully everyone in here knows how to plot. In fact, let me make this larger. Might need more space. Let's make this really large. So hopefully everyone knows how to plot a point. So 1, 2, 3 in the x direction, 1, 2, 3, 4 in the y direction. That gives us a point right here. That's 3, 4. So what it says is that the terminal side of the angle goes through that point. So in other words, there's the terminal side. So terminal means end. So where does the angle begin? Well, this is in standard position, which means the angle always starts at the positive x. So in other words, the angle we just generated is this angle. So that's what it's referring to. So this would be theta. Notice they use theta in the definition. So let xy be a point other than the origin. So our example, we have 3, 4. On the terminal side, all right, we have the terminal side, which helps us determine what the angle is. So far, so good. The distance from the point to the origin is, you might recognize this formula. That's Pythagoras' theorem, just slightly rewritten. So now there's this r that's incorporated based off of x and y. So r is equal to square root of x squared plus y squared. But we know x and y because we were given the point in this problem. This is 3 squared plus 4 squared. And if you do all of this math, you will get positive 5. Because of course 3 squared plus 4 squared is 25. The square root of 25 is 5. So what that tells you, I'll write this in red, is that this tells you the length of so this is the length of the distance from the origin to the point. And you might think, well, why is that important? In this class, I'm going to say something very important. And I'm going to say this throughout the rest of the class. We use something called triangulation. That's a fancy way of saying, with this graph, that point that we just drew, the 3, 4, when we triangulate this, we form a triangle by taking the point straight down and forcing a right triangle. That, when I say triangulation, that is what I'm referring to. We drop the point straight down to the x-axis, and we do that so we can form a right triangle. This is when the opposite, hypotenuse, and adjacent stuff all comes into play. And so what we have constructed down here, I'm going to draw it up here as well. We constructed a right triangle with a hypotenuse of 5. The x value is 3, and the y value is 4, because of course x values go left and right, y values go up and down. And hypotenuse is always the slanted line, the diagonal line. And we did say that theta was this interior angle. So I took the exact diagram from below and I just restructured it above, just made it cleaner. So now our concepts of opposite, adjacent, and hypotenuse can make sense. Because now we have a triangle, we triangulated by forcing a right triangle, and now we're going to figure out the 6 trig functions. Now this is when that SOHCAHTOA stuff comes into play. It's very popular in trig classes. What SOHCAHTOA represents, what is it? Some old hippie caught another hippie tripping on acid. It's a mnemonic memorization technique that helps you remember the first letter of all the correspondences between the trig functions, which are sine, cosine, tangent, cosecant, secant, and cotangent, with their corresponding side associations. So some old hippie, feels weird to say that in a math class, but some old hippie, some is sine, old is opposite, and hippie is hypotenuse. And you can do the other ones for cosine and tangent. So it's a mnemonic memorization technique to remember that. So in other words, sine of theta is, so when I say opposite over hypotenuse, so we're looking at this definition first, opposite and hypotenuse of what? Well, the angle here. So this angle right here, the theta, opposite of it is the segment that is straight across. That's the 4. So it's 4 divided by, what's the hypotenuse? It's always the diagonal line. The hypotenuse is the diagonal line, that's 5. That's sine. Cosine of theta, it doesn't use opposite as its terminology, it uses adjacent. So we're looking at cosine now. So what does adjacent mean? What does adjacent mean in general? It means next to. So not across, but next to. It's the segment that's next to the angle or the side length that is opposite, but it's not the hypotenuse. The hypotenuse is just the hypotenuse. The hypotenuse will not be opposite or adjacent. So it's always the other value. So that will be 3 over 5. Oh, okay. 3 over 5. And then finally, tangent is just opposite over adjacent. We're looking at tangent. It's opposite over adjacent. So that's 4 over 3. So that's 4 over 3. And so those are found. So this is how you notate them as well. It's not that the inputs are 4 over 5, 3 over 5, and 4 over 3. It's the outputs that you're finding. The input is just the angle placeholder. Just like if you were to put f of x. In fact, sine of theta is the same thing as f of x. It really is. X is theta, and the f is sine. So far we have 3 of the 6. In-class people, anything so far? You just following along? Okay, virtual people. All right, so let's do the other 3. Now the other 3 are easier to find if you have the first 3. So you might think, okay, there's 6 in total, so I have to memorize 6 disjoint things. Not necessarily, because you might notice, all right, so CSC is cosecant. This is hypotenuse over opposite. You may notice right across from it, it's just the flipped version of sine. What does flipped mean in math terms? What's the word we use for flipped? Either of you two remember?
It's been a
When you flip a fraction?
been years since I've taken that.
Well, inverse, that's one thing, the reciprocal. So the reciprocal. I'm going to use that word quite a bit. So they use reciprocal in trig, but yeah, inverse is just multiplicative inverse. But yeah, inverse nonetheless. But so the reciprocal. So if you have sine, you just flip it. So that's why these are not part of the SOHCAHTOA. That's why SOHCAHTOA is not extended, because you can notice this correlation between sine and cosecant. That's why even still, when I do these problems, when I think of cosecant, I'll think of just finding sine and then flipping it. You can memorize it like this if you want. I just derive sine and then flip it. Cosecant is associated to secant. So you take whatever secant is and you flip it. So that's 5 over 3, or it's the reciprocal. That's the reason why these are written across like this in the definition. That's the reason why. It's because the associations, the reciprocal, they call them reciprocal identities. That's why they're written across like that, just to emphasize that association. And then tangent and cotangent. So cotangent, it's just tangent flipped. Tangent was 4 over 3, now it's 3 over 4. And that's all 6 of them. If you find the first 3, the other 3 are really easy to find, especially because I do not make you rationalize the denominator in this class. If you don't know what that means, you'll find out later, but I don't make you do that. Okay, so let's go down to example 2 here. So that answers example 1, in-class people, good so far. Okay, cool. So example 2, the terminal side, so it's the same problem, different point. So let's see how much that changes things. We have a new point. So let's go ahead and draw a graph. to draw it in a certain way. Since we're going to have to go to the left, I'm going to make more room for the left part. So going to the left, 1, 2, 3, 4, 5, because we have -5, and then positive 12, just shove a bunch of these in there, you get the point. Still not going to be enough room. One more time. We need a lot of room. A lot of room. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, there we go. That'll be plenty. So we plotted the point. Now we draw, so this is the point corresponding to the terminal side. So that means the terminal side is now pointing to that point. And of course, this point is -5, 12. We triangulate, or you can do this in either order. I'm going to do it in the order I naturally do it. So you triangulate by taking that point and going straight down with it. Just going straight down. So I'm going to use a dotted line. Notice that dotted line. I'm just going straight down because that's how you force a right triangle. You just go straight down. That is triangulation. The angle, since that was the terminal side, the angle is technically this, and they call it beta. So just a fancy looking B. It's a Greek letter, beta. Frat guys already know what this is, but yeah, beta. And so, so we triangulated. We have beta, just like that, because it always has to start. It always has to start on the positive x-axis. That's how standard position works. And it points all the way to here. The good thing about triangulation is that when we view trig functions and when we triangulate, one thing that we did was we forced the right triangle right here. So also, you might notice that beta has nothing to do with that triangle. Well, triangulation means that we can view that angle as a, it's called a reference angle, which we'll learn about later. But using triangle, we're kind of merging two sections together right now, but this is the more intuitive approach. That angle that I just illustrated in red all the way down here, we're pretty much treating that as beta as well. They're not the same angle because they're supplements. But when it comes to trig functions, the trig function doesn't care. So by itself, these angles are completely different. But triangulation, or using a reference angle, as we'll talk about later, allows us to pretty much call that beta. I'll put a little prime next to it. It's kind of, it's not the same angle, but we're going to use them as if they were the same angle, if that makes sense. And we're going to use triangulation throughout this whole semester, so it'll be bound to make sense at some point. Additionally, since we formed a triangle, it would make sense that we start filling in the sides of this triangle. So let's see, hopefully I'll have enough room here. So this triangle, so it's the same triangle, just getting rid of the axis. So we're going to say that the bottom segment is -5. You might think, how does a triangle have a side length of -5? Negative sounds kind of wonky. And the reason why is the representation. This triangle is a visual representation, but in the grand scheme of things, it represents things that may not be intuitive to our interpretations of what's going on behind the scenes. This is just a visual aid. This is along the same lines of how we're able to take two different sized angles and treat them as if they were the same. So this is sort of the caveats of visual aids, but nonetheless, we use -5 because we go in the negative x direction relative to you all watching, I think. I don't know if this is left to you all, but in any case, that's -5 and this is +12 because we go up, and up is a positive direction. Well, how do we figure out the hypotenuse here? Well, we use the Pythagorean theorem. So R is the square root of 12 squared plus -5 squared. Notice I am using parentheses around the 12 and the -5 because -5 quantity squared is +25. If you put it in your calculator the wrong way, you'll get -25, and that's not right. You should probably get 13 here. In fact, you should get 13 there. Probably get the square root of 169, and then that's 13. That's a special triangle, I guess, kind of oddly enough. So in any case, we found the hypotenuse to be 13. And now that we have an angle, and now we have a triangle, and we have a reference angle, which we're pretty much treating as beta, we can go ahead and start filling out. Let's go ahead and start filling out all the trig functions. So sine of theta, or beta, do this in my notes too. Sine of beta is going to be the opposite over hypotenuse of the triangle that we constructed. So of the triangle we constructed right here, the opposite is 12. Just right across from the interior angle. What's the hypotenuse? We found that to be 13. Just keep going. Cosine of beta is adjacent over hypotenuse. So adjacent. It's the value that's not opposite or hypotenuse. It's adjacent. So that is -5 over 13. And so tangent, I'll try to squeeze that down here. Tangent is opposite over adjacent. So that's going to be -12 over 5. Did I lose you? Everyone's good so far? First, let me check. Virtual, cool. And some of you may already be familiar with these definitions and these constructions. If not, just a careful look at them once again. But if anything, knowing the first three means that knowing deriving the other three is pretty straightforward. So what is the reciprocal of sine? That's cosecant. So we can use or find cosecant of beta by taking whatever sine was and flipping it. So 13 over 12. But then what about secant? Well, we take whatever cosine was and flip it. And then tangent. Wow, we'll try that again. Cotangent, it's different. Cotangent. We take tangent and we flip it. And it is okay for trig functions to be negative. In fact, we will learn later on some criteria, the criteria of what makes a trig function positive or negative, just using the quadrant that the terminal side lies in. But that's how you would answer this.
How is tangent, how do you get -12? Tangent.
Well, okay, that's a good question, actually. The question is, for tangent of beta, how do you get -12 over 5? And the reason is, you get 12 over -5, and when you simplify fractions of that regard, the negative just comes to the front of the fraction.
Oh,
That's why. It means the same exact thing. And if you were to write 12 over -5, remember, this isn't my math lab. It's just me grading, and I don't care. You can write 12 over -5 or however you want. So, again, it's not my math lab. I know a lot of you are happy about that. I'm a lot more lenient. Not saying I'm a pushover, but I'm a lot more lenient than my math lab. If you left it at 12 over -5, that's perfectly fine.
Is the first point in the group, is it always adjacent on the triangle or no?
The first point.
On the graph, so how 3 was adjacent?
The answer is yes, because notice how every time there's an X, there's an adjacent. There's an X and there's an adjacent.
Okay.
And same with Y and opposite.
Okay.
So that is a good correlation to make. So if you want to think about it that way, you're more than happy to do so. But yes, X is adjacent and Y is opposite. The question, or the problem lies whenever we get to, we progress on where we don't have an ordered pair to assist us.
Okay.
Because we don't always construct triangles based off of ordered pairs. So when you don't have an X and a Y, what do? And then you have to think about it a second. I'll do one more, we'll call it a day. So, okay, cool. So, all right, so example 3, it's a little bit trickier. Find just 2 of the 6 trig functions and something about a line and then some condition. That's kind of interesting. Well, I don't see an ordered pair, but really what example 3 says is they're giving you the equation of the terminal line. So before they gave us just a point on the line and we drew the line without thinking of the equation. We didn't have to. Now they give us the equation of the line and we're going to find a point from it. So it's basically generalizing a little bit. And lines have an infinite number of points. All we need is 1 point. So technically there's no one definitive answer here. So here it says it just says pick any point where X is less than or equal to 0. Well, I see that it's equal to 0. I'm going to write this in red because this is not going to be good. So we could pick any point such that X is less than or equal to 0. Well, why not 0? Well, why not? If we were to plug it into this equation of the line here, 3 times 0 plus y is equal to 0, and then we get that y is 0. So what's the problem here? Why can't we choose that point? And the reason why other than the origin, cannot pick the origin. Because if so, we can't make a triangle. We can't draw an arrow. We can't do anything. So all of this is gone. All of that's gone. So instead, what about if X is equal to -1? That's the very next one. So if we pick X as -1, then we have 3, -1 plus y is equal to 0, and then y is equal to, well, what ends up being +3. Then we get the ordered pair of -1, comma 3. And I'm out of time, so we can just pick up on that. I made it pretty much as far as I wanted to, so that's awesome. So yeah, I'll leave it there. I'll answer questions in a second. Homeworks 1.1, 1, 2 are both due Tuesday. That upload assignment that I asked you to do, that's due tomorrow. So the upload assignment, make sure you submit it, or makes sure you submit it properly to me. Because on the syllabus, if you don't submit it properly, I'm allowed to dock a lot of points for it. So that's why you do it once and you'll make it a routine. So 1, 1, 1, 2, due Tuesday, upload assignment due tomorrow. It's all in that email I sent out. Any questions in class? You're both good? Online people, if you don't have any questions, you're free to leave. Other than that, I'll stick around, answer any questions.